Good morning, everyone. Welcome to class 487 today. This is the first week of April. The weather is becoming really nice over the weekend, and the air was really clear, even though there was a little bit of rain on Sunday. Let us accelerate a little bit toward deep reinforcement learning. Last week, I briefly reviewed the future of machine learning. I explained that using the figure of our face of human being, as I mentioned before in the previous lecture, probably CNN will represent the eye of our face. Probably RNN and LSTM will be working like our ears, and GPT-3 may operate as our mouth. And GAN and deep reinforcement learning may representing the creative activities of our brain. Those are separate models being actively used in the artificial intelligence society, especially in industry and academia. Even though right now these models are developed separately and working as a separate models, but in the future I believe that all of these models will be combined into a single model that I usually call it as an artificial general intelligence. And it will have multi-functionalities, multi-domains, and multimodal machine learning. In order to develop this artificial general intelligence, as I mentioned many times, we need super strong computing power and semiconductor uh, devices such as GPUs and HBM and DRAMs. In the long future, I believe that artificial general intelligence will be combined with human network, and human network will include the ethics, emotions, philosophy, and religion networks. And then artificial intelligence will work as an artificial human. I strongly believe that it will come to us maybe in 10 to 30 years. Especially in my class, to give you the basics of these models, I'm going to give some lectures on RNN and LSTM. And next week, I'm going to talk about CNN. After midterm exam, I will talk more deeply into GAN and GPT-3. Finally, at the end of this class, I'm going to combine reinforcement learning theory with our deep learning models to explain the deep reinforcement learning. That will be the focal point of our class in this semester. So this week, I'm going to talk mostly about LST, RNN, and LSTM. I will talk about the basic structures and backpropagations and applications. Those are the next few progress uh, being planned in this semester. Now let's start to talk about RNN. RNN represents the current neural network. So um, up to previous classes, I spent most of time to give you the basic understanding and theories to build up the machine learning models. Now it's time to talk about the real model. And I will first start to talk about recurrent neural network architectures today. RNN structure, there are many different ways to explain the RNN structures. I think these are are the very typical and most fundamental way to explain the RNN architecture. First, I'd like to say that it has sequential data input. In the case of CNN, sometimes input will be images, that is the stationary image. But RNN has an input of sequential data. Sequential means it has a time step to 1, T2, T3, to up to TT. In our real life, there are many cases where data are sequential, such as our language or movie or stock movement, stock price movement, or game. Especially in AlphaGo, the game was sequentially conducted. At the end, after 1,000 steps or million steps, the game will be ended. And especially in reinforcement learning, we also have a sequential state. There we are talking about state. But anyway, at this moment, one of the most important feature of reinforcement learning is that it has sequential data. So time is an important parameter of input. As you see in this figure, input has a form of vector. Vector size could be 10 to 16 column or 10 to 19 column. Usually it has very big vector size. At stage T1, it has x1. At stage time step 2, it has vector x2. At time step 3, it has a vector x3. At time step t, it has xt. X can represent an alphabet or word or image. X could be alphabet or word or images. For example, let's talk about word. In Korean language or English, there might be millions of different words, but considering many different languages on earth, global world, my number of words that could be a vector in this RNN could be millions or billions. So X vector could be very large vector. If X is images, in a day, we are seeing many images, probably 1,000 images in an hour. So if we store all the images we see in our whole life, it could be tera scale in number of images. So first I would say that X is a large vector. And it could represent many different identities. Also, T could be range of maybe 10 to billions or more, because if we are reading a book, there will be a sequence of wording in your novel book, and the number of words in a book could be 10 million or 10,000. So T could be also very large number. If we have an input that is connected to hidden layer, in the previous classes, we was showing many theories about deep neural network. We assume that number of hidden layers could be 100 or more than 1,000. So we was able to derive all these forward propagation equations and backward propagation equations. Here also in RNN, we have hidden layers. Sometimes it could be a single layer, or sometimes it could be 100 or 1,000 layers. For the simplicity of class, in this semester, I'm going to talk only a case where we have a single hidden layer. As I just discussed before, the hidden number of hidden layer is not limited. There could be many layers, but for the simplicity and considering the computational power and memory, in recent days, most of RNA structure usually has a single hidden layer. In order to connect input vector to hidden vector, we need matrix W. The W is a kind of weight web matrix. Of course, it is a big, large size. During the backpropagation, we have to optimize the weight matrix W or U. In the basic class of the previous lectures, the data flow from input layer to output layer was we called forward propagation. And when we have some errors, we have to define cost function. Then we were able to derive the gradient descent relationship, and we was able to update this W matrix, and that process was called backward propagation. In RNN, on the other hand, there are two propagations. One is the forward propagation 1 and the backward propagation 2. Interesting thing is that also we have this propagation direction for the propagation 2, and also we have two different propagation backward propagation 2. In practical RNN structure, in this structure, we have two different type of forward propagation, for propagation 1 and for propagation 2. And also we have two different type of backward propagation 1 and backward propagation 2. This makes a little bit complicated to understand the gradient descent and backward propagation and weight optimizations. But as I mentioned before, the basics are the same. In the second week and third week of our class, we spent some time to talk about the backward propagation and gradient descent by defining activation function and cost functions. Here are the same. So it is a little bit complicated, but the principles are same. So I'm sure that you students can easily follow the lecture right now. So if we have a W vector, W matrix, it will make a connection between input vector and the hidden layers. Now, hidden layer output will be connected to output layer using V matrix. It is also a weight matrix. By repeating this forward propagation and backward propagation, we have to update V matrix as well as W matrix by using the gradient descent method. That is the first step of forward propagation and backward propagation. In particular, in RNN, we are going to use logly likelihood the cost function. Some classes before, I was talking about cross entropy cost function as well as log likelihood cost function. Because it is a log nature, it is declining very fast. It has very fast training and near 0. When it is near 1, the cost function is becoming 0. That is the target output. So we're gonna use in the current RNN, mostly we are using log likelihood cost function. Also, we have softmax output function to produce Y, because softmax function has more likely enforcing probability function, so that it will accelerate the optimization time. So this was also we discussed in the previous lecture. So right now, so far, I was talking about for the propagation. We have input vector, we have a matrix W that is connecting input vector to hidden layer output, and hidden layer output will be connected to output through softmax function, and then there will be certain correct answer y dash, that is our target value. At that vector position, we apply the log likelihood cost function. Then we define this cost function. Then we can develop gradient descent function so that we can update V and the U. That is the one direction of RNN for the propagation and backward propagation. Now we have second propagation. We have an input sequence x1, x2, x3, and up to xt. T means the terminal value. The hidden layer output is connected to next hidden layer. That is the big important feature of RNN. Let's assume that you are reading a book. In the first sentence, it may have your name. But sometimes, in order to understand the book, you have to remember the name of the actor up to the end of the book in order to completely understand and figure out the story of a book. So some information, X1, has to be carried up to the end of the book. That is the important feature of RNN. Even though you have very long sequence of input vector, some of information has to be carried up to the end of your hidden layer. So separately, each section may be a DNN. That is what we was talking of for a while in this semester, especially in March. But right now, RNN means that this DNN has to be connected through this W vector, W matrix. Yes, W matrix. So there are three kinds of weight matrix, U, V, and W. W has a function to carry some information of X1 and X2 to the end of Xt. So each DNN is connected through this W matrix. During the forward propagation 2 and forward propagation, backward propagation 2, W is having important contributions. W has a function to carry hidden layer information up to final stage. Without W, it is not recurrent network, just deep neural network. So again, this input information is connected to hidden layer, hidden layer information is connected to output layer. Simultaneously, hidden layer output is connected to second hidden layer. Hidden layer output of second layer is connected to third hidden layer. And output, hidden layer 2 has a connection to hidden layer, output layer Y2. And hidden layer Y3 is making contribution to Y3. So it is a very sequential, but a hidden layer information is propagated to up to the final stage by multiplied by W matrix. So gradient descent means that we have to define cost. Cost is not just single cost. Cost has J1, J2, J3, and Jt. Cost function is also defined as stage T1, stage G2, and stage 3, and stage T. So because of that, the current nature of this Rnn, gradient descent and backward propagation, and those are a little bit more complicated than other models. So now, let me summarize the first slide in this page. First important feature is that it is accepting sequential data. Second feature is that context is conveyed up to the final point. Keep context along the sequence. The meaning of first word or first sentence is not forgotten. They are conveyed through this W matrix up to the final stage. So our language is usually has different meaning depending on the sequence of your wording. Also, you have to remember some wording or meaning of a context text after for long time. T could be a second, or T could be million years or billion years. So those are the very important feature of this Rnn. Another important feature I would like to talk is that it has flexible length. T is not a fixed number. Flexible. T is flexible. It is not fixed. A conventional deep neural network, the hyperparameters are fixed. During the training or development process, you decide the hyperparameters. And then we usually use that for a while, up to some point where we want to modify our model, then we change the hyperparameters. Also, in the previous classes, I was talking about a methodologies to determine those hyperparameters. Sometimes we are using random search, or sometimes we are using grid search. Sometimes we are using hybrid search by combining the random search and grid search. Sometimes when we are selecting data, sometimes we are using the Gaussian distributions. Sometimes also we are choosing data for input data, validation data, and text data. Sometimes we can choose randomly, or sometimes we can have certain algorithm to choose the input data to train your deep neural network. So as I said that usually DNN model has fixed parameters. But in our case, T has a flexible number. Third, last feature is that matrix U, which is used to connect input vector and hidden vector, W, that is connecting hidden layer HT to HT plus 1, and V vector that is connecting hidden layer to output, those are shared matrix. That means that U, W, V are used again at stage 2, and it is being used again at stage 3. It is being used again at stage terminal T. Let's assume that we're gonna use separate matrix W, U, W, V at each stage. It will have huge amount of parameters to optimize. Unless we have very strong computing power, it may be very difficult to do that. So, but at this current RNN model, we are using same matrix, U, W, V, all these sequences. I think these are the overview of RNN. So this is an example, a very simple example. Let's assume that this is the RNN. There should be input data sequences, and then it will have output data sequences, and the hidden layer will propagate through this RNN by multiplying W, and some meaning of this wording will be conveyed to up to the final point. Let's assume that this RNN model is a question and answering machine. I assume that our input is what is your school? And I assume that first vector, what is 0, 0, 0, 1, 0, 0. And fifth row represent what? I assume that very simple representation of vector. Let's assume the second input is is means that vector form of is in vector representation is 0, 1, 0, 0, 0, 0, 0. And third vector is your, that vector is 0, 0, 0, 0, 1, 0, 0, 0. And let's assume that the final input vector is school. The form of school in vector form is 0, 0, 0, 0, 0, 1. And then this vector will become an input vector, and that will be multiplied by U. And the hidden layer activation, hidden layer activation function is usually used tangent hyperbolic function. You remember that tangent hyperbolic function has this kind of classification active shape, and the meaning of X is actually contained in the hidden layer output, and that is multiplied by W. Then second input will be added in this hidden layer H2, and the next input which affects the hidden layer H2 will be input vector X2, that is, and then what is this kind of meaning of this wording will propagate along the hidden layer, and final output layer will be, I assume that KAIST, that vector, I assume that 0, 0, 0, 1, 0, 0, 0. So if we are asking question to this RNN saying what is your school, the answer will be at the final output, that answer will be KAIST. This is another simple explanation of RNN structure. Once again, I would like to say that in this sequential connections, U, V, and W matrix are all same. That give us some simplicity of calculation and network. In this case, I use very simple cases, but vector size will be very large. Vector size, vector and U, V W size will be really, really large. And so even though it has very large size, it will be okay. That is the problem of computing power. So these are very easy explanation of RNN. There are many different applications of RNN. Of course, speech recognition is one area. Machine translation, RNN can translate Korean language to English, English to Korean. Also, when you are talking with the chatbot, there might be some RNN machine inside. So when you are talking or making conversation with the computer, RNN can help you, and conversation is the third applications. Also, it can work as a question and answering. In the previous slide, I briefly showed the example of RNN to give you an idea about the applications, and in those are the question and answering case. Also, input could be an image, then it can generate capturing text message. It can generate text messages. All these are related to sequential data input and sequential data output. Also, in the future, if this RNN can be is combined with GAN, maybe it can create the music. All these applications are related to sequential data input, and the output is also a sequential data output. Also, to give you some idea about the RNN, I also can give you some cases. This is another simple cases. Let's assume that you are typing or alphabet in your computer. Let's assume that you are typing HELLOW. This is a sequential input. In this previous examples, I assume that this vector are representing a word. But in this case, I assuming that this vector input is representing an alphabet. Probably H is represented by vector 1, 0, 0, 0. Alphabet E is represented by a vector 0, 1, 0, 0. L is described by a vector 0, 0, 1, 0. And I assume O is described by a vector of 0, 0, 1, 0. So probably your computer RNN can know your habit or your language style. When you are having input H, automatically it can recommend E. How can convert this RNN convert H to E? There are 4 propagation sequences. This input vector H is multiplied by a matrix U. In other words, we can describe the U matrix W weight matrix XH. XH means W matrix is connecting input X matrix to hidden layer matrix H. WXH meaning that. And then let's assume that hidden layer output at H1 is 0.0, minus 0.1, and 0.9. And I would like to say that this number, 0.3, 0.01, 0.9, we don't know. Just it is a number. Probably some people are trying to explain these numbers. Those are sometimes people are saying that that is explainable AI, but I don't put much emphasis on that. These are just number. And then it is multiplied by matrix V. In other words, I would say V matrix is WHY. That means this is weight matrix connecting hidden layer to output. This hidden layer, so in terms of mathematical representations, hidden layer as stage T is represented by tangent hyperbolic function of input xt. xt is multiplied by wxh, and previous hidden layer is multiplied by whh, hidden layer connection, and the previous hidden layer. So output is a tangent hyperbolic function of input vector multiplied by wxh, that is this term, and hidden layer, previous hidden layer is multiplied by whh, and that is the input of tangent hyperbolic function, activation function. Then it will have a hidden layer output at stage 2, stage T. That is these numbers. At stage 2, hidden layer output is 1.0, 0.0, 0.1, and these are the numbers. In equation, these are diagram type of explanation, but this is mathematical representation of recurrent neural network with respect to hidden layer at stage T. This hidden layer xt will be implied to softmax function, and output will be given. Output. Here, output is 1.0, 2.2, minus 3.0, minus 4.1. If we choose maximum number, second column is 1, other will be transmitted to 0. We neglect other terms, we choose maximum. In the case of softmax, that will give us vector 0100, 0100, this same vector. So output will be recommended to E. If we continue these calculations, next wording will be hello. But if there is some error, in this case, second stage output has the maximum value 1.2, that is corresponding to O. So there are some error between O, right answer should be L, but the output is O, so this is Y and this is Y dash. So there will be some error between output and target output that will be transmitted to cost function, and we will conduct back propagation. These are the another way to explain the recurrent neural network. So far, I was explaining this RNN, the sequential data input, and for the propagation to recommend Y1, Y2, Y3, and Y4. But very important feature of recurrent neural network is that hidden layer information is conveyed to second hidden layer, third hidden layer, up to final hidden layer. It will convey the context and meaning or some information at the beginning of a sequence up to the end of the sequence. In that regard, W is very, very important matrices. In the graphical formations, very simplified drawing to representing the RNA is this figure. It has input vector, it has hidden vector, hidden layer vector, it has output vector. But hidden layer output vector is connected to, again, back to the hidden layer using W matrices. This figure is very simplified schematic to describe the function of this recurrent neural network. As I told you before, this is very simple feature of RNN. There are certain issues associated with this RNN. Number one is that H1 information should be combined to H, maybe millions or billions. That means that sequential number is 10 to 8, huge number. Then W is multiplied, W multiplied by 10 to 8 number. Huge number of multiplication will be conducted during the forward propagation too. Sometimes the meaning of H1 is diminished. Sometimes meaning of H1 is not well combined to H10 to 8. Sometimes, let's assume that I'm reading a book. Sometimes it takes an hour or a day or a week. Even though I carefully read a book, at the end of book reading, sometimes I forgot the first sentence or first page. Sometimes I have to go back to remind what was happening in the past. Like that, sometimes this stage they have to remember what was happening in H1. That is a little bit difficult task. In order to keep this information up to that point, it needs huge amount of memory and computing power, and it will increase the complexity of this RNN. Second thing is that if let's assume that it is image, and sometimes it could be a two-dimensional vector, or it could be n-dimensional vector. So in this way also it may have huge amount of computational time and power. Sometimes, so to simplify this DNA structure, we can use different type of deep learning such as CNN. That is the subject of our class next week or a week after next week. And yes, those are the issues associated with the RNN structures. And so because of that, engineers are trying to develop some modification of these RNN structures. Now let's spend a little bit time to talk about this RNN. This is the mathematical representation of RNN. The hidden layers at stage T is a function of certain input. The function will be activation function. Sometimes we can use Lello function, sometimes we can use sigmoid function, sometimes we can tangent hyperbolic function. There are many different types of activation function. Input will be very important information. Here are saying that hidden layer of previous hidden layer. So current hidden layer output is a function of previous hidden layer and new input layer at stage T and vector theta. Theta represent weight matrix W, V matrix, and U matrices. And these parameters are symbolized by theta. So backpropagation actually meaning that to train theta and using gradient descent method. U matrix has this kind of form. It is. It has a vector x has a form of x1, x2, xd. Let's assume that input vector has a size d, and then U matrix has also, we assume that H matrix has H1, H2, and HP. Then this U matrix is transforming, make a space transition from X to hidden layer. So X matrix has the size of D and hidden layer vector size is P. To convert H matrix to H matrix using U matrix has to have a size of P multiplied by D. So because of that, I would say H matrix H1, HP is equal to U11, U1D, UP1, UPD multiplied by X1, XD. Right now, I'm explaining this process to convert X input vector at stage X to hidden vector at stage 1, H. It will be repeated again at stage 2, stage 3, stage 4, stage T. In mathematical representation, U matrix has a function to convert from X domain to H domain by applying this matrix. This is U matrix and this is X matrix. So H hidden layer output is, of course, here we should have some activation function as I shown up here. So this matrix input has to put into this activation function input, and U matrix has a number of row up to P, and it has a number of column up to D. By multiplying this U matrix with input vector, it will be transmitted to H hidden layer of the size of HP. So because I'm spending this time, because many times, please remember that it is very convenient to remember that X vector has size D and H vector has size P, and the U matrix has the size P multiplied by D. Again, same way, we can make a relationship of W matrix. W matrix is, the function is that converting hidden layer at stage 2 to hidden layer HT plus 1. And W matrix has a form of W11, W1P, WP12, WPP. Because hidden layer has the size vector of 1 to H1 to HP, at T or at T stage, at stage T plus 1 also we have H1 to HP. So it has the same dimension, and this transformation is conducted by using W matrix. Also, we can think about Y matrix has the shape of V11 of V matrix. V matrix P, VQ1, VQP. It has a size of P multiplied by Q multiplied by P, because H1 output layer Y1 has the YQ size is Y matrix has the size of up to Q, Because of that, it has the V matrix has Q row and P columns. It has the size of Q multiplied P matrix. And this V matrix is make a transition from V space to output space, hidden layer space to output space. This matrix, this V matrix is acting as a transformer from hidden layer to output layer. Because of the output layer has a vector size up to Q, the V matrix has the size of Q multiplied by P. This is a little bit tedious class right now, but I'm revealing again this matrix and mathematical representation of this RNN because we're gonna use repeatedly this indexes Q, P, and W, V matrix, and some because I would like to from Wednesday to next week, I want to spend some time to induce the backpropagation equations. In order to do that, you should be familiar with this representation of matrices and indexes. And finally, I would like to summarize my class right now using these slides, these two slides, these three slides. First one is that hidden layer at stage T, this is the then meaning hidden layer at stage T is the activation function output. And the activation function input AJ at stage T is input vector multiplied by matrix U. J's row is a multiplication of J's row of matrix W multiplied by input vector X. And also we can add some bias there. Also, previous hidden layer input vector is conveyed to the next stage AJ, and we have to apply the column element J of matrix W. Column matrix means the WJ means that this vector. This vector has to be multiplied with some input, previous HT minus 1. That multiplication will come to this element. And here, this row and input vector at stage T is multiplied, and that will become an input of hidden layer, a J term. That is this term. So there will be three terms, number 1, number 2, number 3. Number 3 is bias. Number 2 is the multiplication of input vector with U matrix. And this term, number 1 term is the previous hidden layer is multiplied with W matrix column, row J. That will become an input of at stage T, a column, a row is J. That is going to the input of activation function. As I mentioned, that activation function is usually used tangent hyperbolic function. That will be the output of hidden layer T. That means the J's row that is described in this up to here. Now, hidden layer of next stage is multiplied by of course also that is here again. If we obtain the hidden layer, then we have to apply the softmax function. And this H will be inserted to this softmax function. And actually here is the HT is the here is I I would say OT, and then that will be input to the softmax function. And this hidden layer, output layer, O, is multiplication of vector matrix W with the hidden layer plus also bias. So hidden layer is actually coming to this term, and the hidden layer is multiplied with V matrix, and it will become an O vector. O vector is an input of softmax function. Output of softmax function will become the really output function. These are the sequence of another representation of recurrent neural network. And then let's assume that we obtained this output, softmax output, that has the output has a vector y1, and it has output also has a sequential as stage 1, stage 2, stage 3, and stage t up to it has a sequential. Also, we have true value, target value. That this is because this is a supervised learning. We need to have a target value, and a book or library could be a textbook to teach this RNN. Also, we have sequential true value. Then we can define the cost function. Important thing is that cost function is not just simple. Cost function, it can be defined at each stage t. So at each stage we can define J1, J2, J3. So cost function itself is also sequential. So it may go up to terminal. So our definition of cost function will be the summation of a cost function at each stage t up to the final point. This is also a very important feature when we are applying the gradient descent and back propagation. We have to define the cost function. And I would like to say that cost function is the summation of cost function at stage t. We have to summate, add all of them together. There are three different types of cost function we can think about. One of them is the mean square function. I'm sure you are familiar with this right now. Also, we can define cross entropy cost function, or sometimes we can use locally likelihood cost function. This is the end of my class today. As I explained at the beginning of this class, RNN is one of the popular deep neural network model being used in many different cases. It could be used for machine translation, question and answering, or image capturing, and there are many ways we can use this. Up to previous classes, we have spent long hours to discuss about the forward propagation, backward propagation, perceptrons, and gradient descent, and cost functions, and activation function. Now, I would like to combine all of those previous understanding of basics to explain this RNN. RNN is a little bit complicated than conventional DNN, but because it is used quite frequently, I think it is good to understand the basic structures and mathematics and connections and so on. In that regard, today I give overview of RNN today. From Wednesday and a week after that, I'm going to give you spend more time to use these equations that is explaining the cost functions and all these equations. I'm going to use all these equations to derive the update equations. Especially as I talked to you, emphasized many times, we have two different type of propagation. This way we have backward propagation and forward propagation. Also, we have to think about of propagation in the time domain. In sequential domain, also we have to apply back propagation to update the matrix, especially W and U and W matrix should be updated considering back propagation 1 and back propagation 2 together. It is a little bit complicated process, but basics are the same. Thank you for your kind attention. And next class, I'm going to spend more time to talk about back propagation and back propagation 2. Thank you.